You're all welcome to this first lunch talk, Transport After COVID-19. And today I have the privilege and the honor to introduce Professor Hens, who will talk about the mathematical models of SARS-CoV-2 for Belgium. Just a few outlines for what is coming up next for the association. So remember that the Transport Research Days will take place on May 27 and 28. We decided that the conference will be held online. And the next lunch talk about the COVID activities after transport will be on April 30, where in the continuation of the talk of today, there will be a discussion on the vaccination centers from a logistical and geographical perspective. So I'm happy to pass the floor now to Niel. So.
Okay, if all goes well, you can see my screen now.
Yes.
I'll put that in presentation mode as well. Okay, there we go. So thank you for the invitation, Mario. Good afternoon, everyone. So I thought a little bit about what to present today. It's kind of difficult in a sense because we've done quite some work related to the COVID-19 pandemic, and especially also in the Belgian context. So what I did was, my focus will be on the mathematical models, and maybe we can take the discussion from there, because I'm very eager to interact with you, and also definitely because you're all working in, or most of you, I think, if I'm correct, are working in mobility. And so in that sense, well, I have no clear-cut answer to many of the questions related to mobility, but I'll give you a little bit of a notion of a model that we've been using, first unsuccessfully and then successfully in terms of mobility and the spread of COVID-19. And then maybe some ideas and some thoughts, and maybe some also definitely ideas towards the future, let's say. When I'm talking about what we've done, I'm talking about the CIMIT group. CIMIT group is kind of an informal consortium between two research groups at the University of Antwerp and at Hasselt University, and I'm kind of the physical link between both, because I have an affiliation at both universities. And so it combines the group working on infectious diseases within the Center for Statistics at Hasselt University, and which I'm leading, and then also the Center for Health Economic Research and Modeling Infectious Diseases, which is led by my colleague, Professor Philippe Beutels at the University of Antwerp. Philippe is a health economist. And in the years, we've evolved from a group of 4 persons. Now, I think we're about 30, 35. It depends on how you count. With people ranging, well, crossing or ticking the boxes in terms of the areas of immunology, of infectious disease modeling, both within host as between host, and then also the health economic evaluation of, for instance, vaccine programs, but not only related to vaccine programs, but also more in general. Maybe you've heard of some of our work in the past, maybe you haven't. We are very active also internationally, but also nationally. And we've given advices to the Federal Knowledge Center for about 9 infectious diseases. And that's so that's maybe if I can ask people to mute unless they're talking. Okay, thank you very much. So to set the scene a little bit, I'll talk a bit about mathematical epidemiology and where it's coming from. And so I do this in every talk because I think it's really important. And some of the discussions that we have today are actually discussions that were already taking place in the 17th century. And so that's definitely something that I want to make you aware of. Oh, sorry, the 18th century. Then I talk a little bit about the data that we're using and the analysis as such, and the way I look at science within a crisis like this, or during a crisis like this, and what that all means, and maybe some of the things that are not very clear also for the media, because they typically think that these are the boring stories, but from a scientific point of view are very, very interesting stories, and a very interesting take on how to deal with the pressure you're dealing with during a pandemic like this. That is, I think, really important to set the scene as well. I'll talk about 4 models that we started developing, the meta-population model, an individual-based model, and a stochastic compartmental model, and the success and the failures of these models, let's say. And then I'll move on to what is what you maybe have seen last week in the press conference by Steven van Gucht and Yves van Latem on variants and vaccination. Well, I'll show you where we are at this moment in time, and I'll end with some short note on models and communication, and what are the pitfalls, let's say, and maybe illustrate one bad example, let's say. A bad example that also endangers the interpretation of models brought forward by this bad example, this group of people that actually failed to do something at first, but now are seemingly catching up on things. But their reputation has been hampered by what they've done initially during the pandemic. I'll come back to that. So first of all, Niel is really the founding father, let's say, of mathematical epidemiology. Niel lived in the 18th century, and he developed, well, he was, of course, member of the big family of Bernoullis. And he actually developed a mathematical model to describe the spread of smallpox in a population at that time, and that was France. In his mathematical model of smallpox, today we would actually write that mathematical model with 2 differential equations. I haven't put them here because that's not so important as such, but the key factor that he wanted to actually, or what he wanted to do, was really with this mathematical model describe how smallpox was spreading through the population as such. And he was actually looking at what it would mean if smallpox would be eradicated from the population. So basically what he did was, with his 2 differential equations, he described what was going on at that moment in time. And then he took smallpox from the equation, let's say, and looked at what the impact could be on life expectancy. And what he found was actually that the median life expectancy, and the life expectancy is a bit kind of a difficult term because life expectancy is always an expectation. But when he looked at the median life expectancy at the individual level, he could actually show that it would actually increase with 10 years if smallpox would have been eradicated at that time. That would mean that 50% of the population at that time would actually live 10 years longer if smallpox would be eradicated. Now, what was eradication of? How could you make smallpox go away, let's say? That was really by inoculation with cowpox. Inoculation with cowpox itself, however, is a dangerous affair. It sometimes leads to people dying because of this inoculation, not at the same rate as people die from smallpox, but nevertheless, it was of a concern. And that is actually the origin of a dispute with Jean Le Rond d'Alembert, a famous mathematician. And Jean Le Rond d'Alembert, what he actually did was, well, he indicated that he brought forward the concept of individual choice versus what is good for the population. So the individual perspective against the population perspective, which is really something that we're dealing with today. I would say less so about vaccination, although indeed, of course, the vaccination debate is currently ongoing, but primarily in the fact that we have measures that are taken at the population level, and these measures are not fine-grained. They're not oriented towards specific people as such, and therefore people criticize the measures as well. And I think we all know the examples of the curfew, for instance, where some people argue, well, this curfew, that doesn't make any sense. If I have to walk my dog late in the evening or at night after 12, I'm not disturbing anyone and there is no risk of infection. And of course, that's true from that individual perspective. But we know from the epi perspective and about people's contact patterns and mobility and so on, we do know that evening contacts as such are actually quite, could potentially be high-risk contacts. So a curfew from an epidemiological sense, from the principal point of view, let's say, it's very difficult to really unravel how much the contribution would be, but it actually does make sense. And that conflict between those two is actually also a very lively political debate at this moment in time. For me, it's the wrong question. Whether a curfew works or not is the wrong question. For me, the question should be whether the curfew is a proportional measure. And that's a different question to answer. But I will not go into that too much now. But actually, let me come back to Jean-Laurent d'Alembert and Daniel Bernoulli. Although they had a dispute, and yes, of course, it's always jealousy that also plays a role, they were both in favor of inoculation, and actually inoculation to prevent smallpox from spreading and causing huge amounts of mortality, let's say, at that time. Now, so Daniel Bernoulli developed this model based on two differential equations. And it's actually the same thing we're still doing today, looking at counterfactuals. What would happen if we do this? What would happen if we do that? And the main reason why we do mathematical modeling, well, there are two main reasons. First of all, we want to forecast. We want to see what would happen under certain scenarios. And the second thing is we want to better understand how the disease is transmitted. And I think both have been successfully used during this pandemic, especially when you think about forecasting. I think we've done a fairly good job with the models that we've been using in forecasting. And forecasting is not, in my book, is not prediction. That's a different thing. Forecasting is really coming up with scenarios, because it's very hard to predict what will happen and how people will change their behavior. And that's not what we're trying to do. We're trying to show what would happen if certain policy decisions are made. In terms of understanding, for instance, the one thing that I find very striking still is the assumptions about how transmissible children are as a vector in this pandemic. And the assumptions that we made initially in the first wave and what followed more than a year ago now, these assumptions still hold quite well. They hold to a large extent, let's say. It has changed a little bit because of the new variants, but as such, it does hold still today. And that's remarkable because we didn't have a huge amount of evidence for that. And still, it fits the bill, let's say. Of course, we're developing new insights, more insights, and so on, which is also very crucial to get a more detailed picture of the role of children in this pandemic. And I'm happy to discuss that in more detail. I will not do that right now, but happy to do that later on as well. Now, this picture is taken from the book by colleagues Matt Keeling and Pesh Rohani. And what I find this drawing very nice to illustrate one thing that we're always confronted with. And that is actually, so on the picture, what you see is on the horizontal axis, we have time since infection. On the vertical axis, we have a measure of an amount of pathogen, let's say. Typically, people would calculate viral loads as a proxy of the pathogen multiplicating inside the body. But at a certain point, you see also this solid black line. The pathogen actually wins the battle, the immune system wins the battle, and the pathogen starts to diminish later on. And according to that schedule, you can actually put people into boxes. It's, of course, that's a very discrete way of doing it. And you can do it in a more continuous fashion, but people are susceptible until the moment they get infected. And then the pathogen actually starts replicating. That's kind of a discrete event at the moment of infection. And then people start, this pathogen starts replicating in the body, and people will actually become infectious after a while. So first, when infected, you are not yet infectious. you're actually what we call exposed or latently infected, but you cannot shed the virus or give the virus to others. But at a certain point, you have enough virus to share, let's say, and you are infectious and you will be able to transmit the virus to other individuals that you come in contact with. Now, after your immune system wins the battle, let's say, you will be recovered. And yeah, there are different connotations of what recovery really means, and it's still an open question also for SARS-CoV-2. But we could actually argue that this picture is an approximation of what would happen for SARS-CoV-2, at least in the early phase of a pandemic that like the one we are experiencing at this moment in time. Now, these different compartments are what we call the infection status. So people are either in the susceptible class, in the latent class, in the infectious class, or in the recovered class. And this is kind of a general picture. It's not really devoted to SARS-CoV-2 yet, and I will show you a picture of that in just a moment. But the key issue that I wanted to bring forward here is that the infection status is something that we can model almost perfectly, let's say, in terms of mathematical models as such. And there are many options in terms of mathematical models, and we'll come back to that later. But this is something that we can do fairly well. What is the key issue, however, is what are the time periods that people are exposed? What are the time periods that a person is infectious? Or when is a person recovered? When can you call a person recovered, and so on? And that is the difficulty there, is that you really need to inform that with medical data or medical status data. And you know very well every day what we hear in the media is also the announcements on the number of confirmed cases, the number of new hospitalizations, the number of deaths, and then also the number of people in hospital, the number of people in the ICU ward, and so on. And all of these data streams, all of these time series are actually incomplete in some sense. They're all a picture of what is truly happening, and what is truly happening is actually contaminations. Contaminations is something that we want to learn from and what we want to observe, but we don't observe it. We see, for instance, the confirmed cases. And the confirmed cases, well, that's only those people, of course, that develop symptoms or that have been actually tested because they are in either in a kind of a surveillance program, as is the case for some settings. Think about the soccer players, first division, but also because of contact tracing with high and low risk contacts and which of those contacts are being tested. But of course that, well, all these data that you acquire from the confirmed cases are always prone to reporting issues, reporting delays, underreporting, health-seeking behavior, for instance. And for instance, we know we have an upcoming holiday now, and we know that people will not seek help directly in a holiday period, simply because they do not have to show to their employer when they have a holiday period that they're absent due to illness. And these are small things, but they all distort that picture of what these confirmed cases really mean. Now, that makes life very complicated. And therefore, in what will follow, I will show you the work that we've done, and we built that work upon looking at what the number of hospitalizations really were as a most stable indicator within this pandemic. What is very crucial also in this picture is the overlap between the incubation period, which is the time between time of infection and the time of symptom onset, and the infectious period. And that actually what that means is that there is an overlap. The overlap there actually means that there is what we call pre-symptomatic transmission. And that's one of the crucial factors for SARS-CoV-2 compared to SARS-CoV-1, compared to MERS-CoV, compared to Ebola even, is that the overlap between the incubation and the infectious period is not there for those other viruses, but it is here for SARS-CoV-2, and that's why it actually had the potential to become pandemic, simply because people will actually spread the virus before they develop symptoms, and therefore they will not refrain from making contact with others. That's the same. It's actually the reason why, for instance, Ebola typically cannot spread very fast. We have seen counterexamples of that, but that's really because of distorted health systems rather than anything else. So let me not go too much into detail there, but one of the first things that we've done more than a year ago now is we looked at what is the extent to which there is pre-symptomatic transmission. And we actually discovered, along with other groups that discovered that at the same time, more or less, using data from Singapore and Tianjin in China, we actually discovered that the pre-symptomatic transmission was really quite high. And in the study, we actually estimated it to be 60 to 70%. But you need to be careful in interpreting that because it was also biased because of intervention measures in these places. So today we would estimate that people that will eventually develop symptoms can actually infect up to 30% of the secondary cases during that stage where they didn't have symptoms yet. And that's a lot. That's quite a lot because that's something that is very difficult to contain, let's say, by pharmaceutical interventions. But nevertheless, it actually shows that preventive measures are also very important to stop the spread of SARS-CoV-2. All right. So the tricky thing is really to get this mathematical model informed by the right set of data. And one of the crucial things is in infectious disease epidemiology, which is different from non-infectious disease epidemiology, is that we all have interdependencies. These data are by definition correlated. They're also by definition incomplete because we do not observe all the transmission events and so on. What we can observe, what we can actually go for is proxies of that, but not the transmission events as such. There has been, for instance, a very extensive discussion about what is causing the spread of SARS-CoV-2. Is it droplet transmission? Is it airborne transmission? And we've seen people taking stands on both extremes, let's say. It's only droplet transmission. That was really the claim initially during the pandemic. And people saying, well, it's only airborne. It's only aerosol. And the truth is, of course, this is a continuum. It's not discrete, it's a continuum. And you have to take both into account. And that's a stand we've always taken from the very start. And especially people who are already working in the field for quite some time have taken that stand, because this is, of course, also very well known for influenza and other viruses. But it makes things quite difficult if, because a lot of the knowledge is still not as granular as we would have hoped for. And also the difficult discussions about outside contacts, are they completely safe or not? Well, some people would say, well, they're completely safe. Well, again, it's taking an extreme stand on things, and it's not really true because there have been documented cases of outside transmission, making it a much more subtle discussion than just saying, well, whatever you do outside is safe. On the contrary, whatever you do inside is unsafe. That's also not true. It all depends on conditions, and that's something quite difficult to deal with. And why is it so difficult to actually discern or take a very granular stand on this? It's because we're always dealing with observational studies. We're not experimenting with our populations. At least that's not the idea. And observational studies are, of course, prone to biases in terms of reporting, in terms of the disease process. And of course, the claim that association is not causation has been used quite a lot. But at the same time, an association should also be explained. If you see an association, it could be a coincidence. But of course, there are epidemiological principles, and then association is not only coincidental, but it's really about a signal that is there. And that brings me to the basic scientific principles of conjecture versus refutation. And what I've seen, and that was, to me at least, quite astonishing, really, is that some scientists have taken the wrong angle at this, honestly. And that's, of course, it's more a philosophical discussion. And it's kind of, it reminds me also of Daniel Bernoulli and Jean-Laurent d'Alembert, because also that is more of a philosophical discussion. And these discussions were already there at that time. They're also at this time being taken forward. But it's good to have these discussions, but it's actually, it shouldn't be used in the wrong sense, let's say. And I think we've seen quite a few examples of it being used in the wrong sense. And so what for me is very useful is to look back at what already exists in terms of evidence-based medicine. And then you go back to Bradford Hill criteria, which actually express a confidence in causality. They're not there to show causality, they express a confidence in causality. So that's a difference, which builds further up on the work of Robert Koch, looking at in microbiology at causality as such. And if you believe there is a causal relationship, well, then there is a series of consequences to that. And that's actually what Bradford Hill expressed in the criteria he brought forward. I'm not going to go into detail too much, but I wanted to bring this to the table because I think it's a very difficult and an often misunderstood issue in dealing with this pandemic, and especially when thinking about the management of this pandemic. On the right-hand side, I've shown two pictures of two books. One is by a colleague, Niels Becker. And what Niels has done in his book in 1989 is very nice. He uses martingale theory, which is a little bit more complicated, and therefore I think the book is less well known to people. Because also Niels Becker's training is really in statistics and quite theoretical statistics at first, but he also has a second edition, which is a little bit more approachable nowadays. And I just wanted to raise the book because the martingale theory is really there because of the difficulties in terms of dependency. And that's why, yeah, you need a little bit more theory, you need a little bit more theoretical construction of what you're doing, basically. And then I also like to mention the book I co-edited with my colleagues Leonard Held, Philip O'Neill, and Jaco Wallinga, the Handbook of Infectious Disease Data Analysis, which actually was published last year, well, 2 years ago now, in 2019, at the end of 2019. Very coincidentally, but it covered a lot of topics, and a lot of topics which are really relevant for today in the analysis of infectious disease data arising in this COVID-19 pandemic. And a lot of the contributors in the book are also key players in the pandemic response at this point in time. So maybe the names don't ring a bell to you, but Ben Cowling, to say one of the names. Ben Cowling has contributed to the book and is also one of the persons that was heavily involved in the first analysis of the data that came back from Wuhan. Just to illustrate this. Some of the chapters have been made available free of use from the publisher, which we really encouraged, and are really relevant for everyday work nowadays during this pandemic. Now, I'd like to end this introduction, let's say, with a quote by Bradford Hill, which I think we really should live up to during this pandemic, but which also raises some issues, of course, because it's a little bit unsettling that sometimes scientific evidence is accumulating, and therefore some of the initial ideas have changed. Not a lot, but they do. There are some things that did change during this pandemic. So I'm just going to read it for a moment. All scientific work is incomplete, whether it be observational or experimental. And all scientific work is liable to be upset or modified by advancing knowledge. That does not confer upon us a freedom to ignore the knowledge we already have, or to postpone the action that it appears to demand at a given time. And it actually is a call also for, if you criticize people, criticize them within the context of this knowledge that is there. And of course, I think we are all aware of that this is in normal times, we also do this. But in a pandemic, life goes a little bit faster. And I just want to, well, I'm still thinking about this a little bit in the moments that I take some distance from the work that we're doing. And I think we've been doing very rapid science, and rapid science is also dangerous as such, because you could be wrong. So there's a lot of time pressure. The context is extremely important, more than the results sometimes. And that has been taken up by the media sometimes in the wrong ways. That's also something that we have learned during this pandemic. Of course, this was already known, but it really came above as being an issue. Assumptions are important, and we term this as early evidence. And early evidence is always a call out for more evidence needs to be accumulated, more evidence needs to be gained. And of course, it comes with a lot of uncertainty still. One study today is not worth or is not telling you the truth, especially when things are evolving very quickly. You need a body of evidence for certain claims to be looked at. And the example there, as I already indicated, was the role of children, which was established in a very quick way, but actually which nowadays still stands, which is not black or white, it's really gray, it's in between. I will not go into detail now, I will not, but we can for sure go into that faster, later on. And then I think the second bit is slow science. Now, slow is maybe the wrong word, maybe I should call it slower science, but it's actually the rapid science looked at again in more detail, looking at what happened in different countries, for instance, looking whether or not this rapid science, which is about maybe one study, can I generalize it? What are the conditions to generalize it? And so on. And an example there is, for instance, contact surveys. So we've been collecting data from different contact surveys, also thanks to the work package leader in the EpiPost Horizon 2020 project I'm coordinating. And this work package leader is the London School of Hygiene and Tropical Medicine, John Edmonds, as a PI, who has a huge expertise in this field on contact surveys. And the idea was there to look at contact surveys and to look at how meaningful they are to describe the spread of SARS-CoV-2. And actually what we found was they're remarkably accurate, which is amazing because that is something that we did not anticipate in that way. We successfully used them in the past for instance, H1N1 in 2009, but the way they have been able to explain what we saw for SARS-CoV-2 has been really extraordinary, and I'll come back to that in just a moment. And then, of course, so slow science is still faster than usual science, let's say. So in that sense, things have been evolving quite quickly, and a lot of the rapid science has actually been confirmed by the slow science, but also slow science has actually contradicted some of the rapid science. And I think we all know the example of hydroxychloroquine as a possible treatment. That hasn't been proven very successful, although people really quickly switched to it. Also, remdesivir had a huge potential at first as an antiviral in this context of this pandemic, and it has been shown not to be as potent as people hoped it would be at first. So yeah, that puts things a little bit, for me at least, into a context. And then for preparedness, I think we can do a lot more. I think nevertheless, we actually made a lot of progress over the past decades. And I'm thinking about the different pandemics and epidemics that I was involved in, also in international research. So I'm thinking about the pandemic in 2009, H1N1 pandemic. And I'm also thinking about Zika. I'm also thinking about Ebola in West Africa and now in DRC. And this international community is really a strong community. And I'm really proud to be one of those people that can reach out very quickly to other people in other countries. And I think we know very well what the whole discussion about COVID-19 and Sweden was. And I really advise people then always to contact people in Sweden to talk to those people. What is going on there and what are the differences, for instance, with Belgium as such, but also with other countries. And it's not that easy to compare things. And so all the the opinions that people have actually casted about Sweden, they should be nuanced to a large extent. And that is something that I could reach out to a few colleagues that I know very well in Sweden that also indicated that in Sweden, for instance, the potential for SARS-CoV-2 to spread very fast is actually lower than in Belgium. And that actually also explains to some extent why they had an easier time of dealing with SARS-CoV-2 as such. Again, I will not go into detail too much, but we need to actually understand that much better. And we need to think about that towards future pandemics as well. And an example that we're currently looking at is to look at demography and to combine it with disease modeling. So we have developed a demographic simulation model for Belgium that we're now looking at, and we're trying to actually, well, first work that we've done a review, and now we're actually continuing with the model that we've developed for Belgium. And the question we are posing ourselves is, what would have happened if this outbreak did not take place at this point in time, but in 20 years? And that's a useful exercise because we are in an aging population, and we also know that households will become smaller over time. That is also a demographic trend. And so we are actually expecting in several decades to have many more people of single person households, which is actually very important in terms of if you think about disease spread as such. And the other thing that we've been looking at with this model is also the role of the size of the nursing home in this pandemic. It's a no-brainer, like intuitively maybe, but of course you want to make this more tangible in terms of numbers. What would happen if nursing homes would be halved in size? What would that mean in terms of how many people would actually get the infection and in terms of the spread of the disease in nursing homes themselves? So these are kind of the things that you need to work on all the time, and I think we need to step up there, and especially from the European perspective, let's say, and especially if you compare that, for instance, to Southeast Asia, where some countries are really well prepared. And maybe we can talk about different structures and different regimes and so on, but nevertheless, we could learn a lot from those comparisons. Now, let me get to the models of SARS-CoV-2. So we developed statistical and mathematical models. I will not talk about the statistical models today, but I would nevertheless like to mention one of the models, which I think you probably find very interesting, is a short-term prediction model by my colleague, Professor Christel Faas at Hasselt University. And what Christel has done, she looked at what is the best predictive model for the number of new hospitalizations. So if I look at the data today, can I predict what will happen in the next week to come, in the next 2 weeks to come, without intervention measures in place? That's really this would be really a predictive model if there will be no interventions as such. And what she actually found or established is that the positivity rate, one of those time series that we get on a daily basis, is linked to mobility data. And if you link those two, you can actually predict fairly well what would happen in terms of number of hospitalizations in the next few weeks. Now, mobility data, I have to specify the data that we are using is Proximus data. Of course, there are pitfalls with those type of data and so on. You can also use Google mobility data, and you can actually go into more detailed layers and so on. And it's an exercise we've done to some extent, but not to the extent that we would have hoped to do. And I think we need to learn more about that as well towards the future, as in particular. But I'll come back to that also in a short moment when I talk about the metapopulation model. So before I do that, I have to tell you that we started with 3 mathematical models. Why 3? Why not 1? Isn't that difficult enough, and so on? Well, 3 because we basically already had 2 out of the 3 models ready. not for SARS-CoV-2, but we could easily adapt them basically to SARS-CoV-2. So, and that was the meta-population model, which we developed early on. And we actually published a paper about that in 2018 for the spread of influenza, seasonal influenza in Belgium. And that worked pretty well for influenza. I'll come back to what that model really looks like. That paper is now in a minor revision for BMC infectious diseases. So I'm quite sure actually that we'll be able to finish very soon there. Then the individual-based model STRIDE, which we previously have used for measles, for instance, because we were really focusing on measles and the eradication of measles in Europe. And in particular, of course, we were looking at Belgium. STRIDE at that time was a simulator for 3 million people, and we actually scaled it up to 11 million for two reasons. One, for scientific reasons, so that indeed sometimes you do see scale effects and you want to take that into account. So if you just ramp it up from 3 to 11 million, sometimes that does change something in terms of the disease dynamics. So you need to take that into account. And the second thing was also because conveying the message about 3 million, people will stumble over the 3 million instead of the 11 million, if you want to explain how a model like that works. And that's, of course, of secondary importance, but in communication, that is nevertheless an important aspect. I'll come back to that in just a moment as well. And then the final model, and that's the model that maybe you've seen on the curves from on the press conference that I've given with the Prime Minister, but also a press conference of Steven van Gucht last week, the stochastic compartmental model. And this is kind of our reference model. That is the model that the government also recognizes as being the model that they follow as such. And there I need to stress always that this is, of course, not the only model. There are assumptions underneath, and you need to be careful not to overinterpret it. That's another challenge, actually, that needs to be taken care of. Now, very briefly, what is the meta-population model? Meta-population model is the model where we look at Belgium. We look at all the municipalities in Belgium. So we're modeling patches. The different patches are the municipalities in Belgium. And we look at modeling the infection within the municipality, but then also looking at mobility between municipalities. And in the past, we've done that using census data and mobility data. We've also developed this model for France, where we also used similar data. How do people move when they go to work, when they go to school, and so on? How they do move from one patch to the other patch. This happens twice a day. That's the resolution of the model. You can, of course, increase that resolution. But it actually means that people move in the morning, let's say, they move to work, to school, and so on. And in the evening, they move back. And during those 12-hour time slots, people interact with each other according to a stochastic compartmental model. And I'll explain that in just a moment, how that works. But by the fact that people are interacting with each other, move from one place to another place, you're trying to mimic spatial spread of a disease. And as I indicated before, for influenza, that worked really well in a 2018 publication. And honestly, for SARS-CoV-2, we had trouble making this work. And so this was the first model we started using, also because we were collaborating at that time, and we still are in discussions with Vittoria Colizza of INSERM in Paris, where they are also looking at a metapopulation model. And we actually failed. We failed also in Paris or in France. The metapopulation model did not do the job, let's say. And likely, and that's one of the key things that we want to investigate further, is the reason or the way we took into account mobility as such, and how that relates to really high-risk contacts and high-risk behavior. It's not because you are mobile that you are having high-risk contacts. So I'm now working at home, but if I would move to my office in Diepenbeek or in Antwerp, I would be alone. There is almost no one else there. So you will not necessarily make contacts there. Whereas in pre-pandemic times, let's say, when you move, typically you move for making contacts. that is kind of the relationship between time use data and data on social contacts. And we do have some good data about that from a survey we've done in 2010, but that picture, I think, has changed during this pandemic, and that's something very difficult to tackle. Now, after a lot of tweaking, we made it work, basically. You have to be careful with the interpretation, but we need to further dig into details to see what is spatial spread and how mobility data and so on, how they get along in more detail. Now, what did we do with this model? As such, we evaluated the exit strategy after the first wave. And I think we've done that successfully. So I will not go into detail here, but on the top picture there, you just see the fit to the initial peak. Those are the black dots, the observed number of hospitalizations. And then you see the other dots a little further on, and that's actually what the green line is what the model said it would do. And the observations are very consistent with what the model actually predicted. How did we come to that? Well, we came to that looking at different scenarios and then considering these scenarios and then comparing these scenarios with the observations. And that has been very useful. Why? Because we learned a lot by looking at those things. So one of the first sectors that reopened after the lockdown in last year in March and April was the B2B, business to business. And one of the key questions was how many contaminations would that actually resemble? That's very difficult to measure or to quantify because a lot of intervention measures were already in place. A lot of preventive measures like shields, like distance, like ventilation and so on were already in place. And actually that was really successful. B2B at that time had no impact basically on disease transmission, except for a few exceptions like meat companies and so on. So I think we learned a lot from looking at this model at that time, but it was not the model we could use at first. The model we first used was actually this individual-based model, STRIDE. STRIDE is an individual-based model, like I indicated, with 11 million individuals, where people are organized in households according to age distributions consistent with the census data. People also travel distances and go to school and interact, like children interact with each other. We know that it's closer to home for pre-primary school, for primary school, and then you go further away from home for secondary and tertiary education, and that's all included in the model. We have some general mixing places in the model. We also have workplaces in the model. What is not in the model at that time, we did not have nursing homes in the model. That has been changed. They're now also in the model. And what we're trying to do towards the future is also to develop it further. For instance, to take hospitals into account, have spatial structure into account, and so on. But that will be work for a few years, I think, to come. Now, what did we do with this model as such? We were actually able to explain with this model fairly well what was going on during this first lockdown. And the reason why this model actually worked better than the metapopulation model, I think, is the fact that we are dealing with SARS-CoV-2, which is a super spreading disease. So if you have the right conditions, basically, one person can infect quite a few people with this virus. And that is known in epidemiology as super spreading events. We typically try to avoid using the term super spreader because it's really the conditions, the environment, and of course also the viral load of the person that is actually contagious at that moment and the number of contacts that person makes. So it's not all due to that person that super spreading really occurs. And that's why people don't like to call the individuals that are involved super spreaders as such. But what super spreading really tells us is that 20% of the individuals are causing 80% of the infections. That really means that a lot of individuals are not causing any secondary infections, which is really good in terms of spread of epidemiological spread. That's really good. Of course, what is the disadvantage is that large gatherings and so on are not safe. Large gatherings need to be avoided, especially when they take place indoors. And when there are no masks and ventilation are an issue and so on, then you have large problems with super spreading events. And so that's likely also why, for instance, in the summer to come, these type of large events cannot yet take place, and they will likely take place, hopefully, quite soon and quite fast, but as soon as it's safe. But it will not be before August, I think, that it takes place. Of course, we need to monitor this, and of course, if it is possible to organize them in a more or less safe way, that I think everyone will enjoy that again. Now, two things that we've looked at with this within the paper by Lander Willem in Nature Communications is the impact of what is called the household bubble. And I think you all have heard about the household bubble, and some people have sacrificed the household bubble, let's say, in the media, saying it was not, there is no epidemiological reason for that. Well, I provided some input for the fact check, because actually also the modeling here really shows that household bubbles are really a sensible thing to do. Also because of the super spreading, actually. Why? Because the simple idea was, during this first lockdown, we got a lot of messages, and I got a lot of messages saying people are lonely, especially people living alone. Well, then the very simple idea would be, what would then happen if you team up these people as to form a new bubble? And you take the same persons, you only have contact with the same persons, you're not switching contacts and so on, so it's a stable connection that you take for a period to come. And actually that makes a lot of sense. So what did we do in a model? We simulated what would happen if you would do that in a random way, linking up to other individuals, like you would do in normal times. And you compare that with the household bubble approach. And we compared it with joining 2 households, 3 households, 4 households, and so on. We also looked at the age of the parents in the household, if it was a household of larger size. Not when you had individual households, but then also that played a role in terms of hospitalization. So you should always avoid intergenerational mixing, basically. That is also something that came out of the work that we've done. But the gray area in these plots is the area that actually was the set of possible outcomes in terms of the simulations. And you could really lower that to the blue scenarios if you do household bubbles. And the different blue scenarios are really household bubbles of sizes 2, 3, and 4. So you see, for size 4, you go up again, but as long as you stick to 3, you're more or less okay. In the second plot, we've looked at something else, and that's contact tracing, and how fast you need to be in terms of contact tracing as such. Now, this is actually depicted in the pictures above. So what we did is we really simulated the process of contact tracing. Now, time is of the essence, and I think everyone is aware of that. But why is this then useful to look at? Well, of course, the logistical constraints are always very important in the whole contact tracing story, but it does give an indication what we do. It does give an indication how fast you need to be. And a second thing, and especially when we were confronted with the second wave, there was the question in the contact tracing in the call centers, who do we need to approach? Do we need to approach as many index cases as possible? Or do we need to approach as many contacts as possible? And actually, we could answer that question using this simulation to say you need to actually focus on the index cases as such. So that is an exercise we've done. And again, we had 3 scenarios that were much better than what you had if you would let it go and if you would simulate it in a regular way. In the last picture, that shows actually the combination of the bubbles and the contact tracing all together. And that would be extremely efficient, actually, as a means of containing or mitigating the spread of SARS-CoV-2. Sorry for the noise. That's working at home and someone else is printing and the printer is next to me, so apologies for that. All right. Then the third model that I talked about was this this model in the stochastic compartmental model. And that model, and I'm showing the compartmental model on the left-hand side with all the compartments. This model is also underneath the compartmental model as a principle, is also underneath the individual-based model and underneath the metapopulation model. So what do you assume? People are first susceptible to infection. They can then be exposed. They're not yet infectious, so they cannot spread the virus yet, but they are already infected. And then once they are exposed, they go into the pre-symptomatic infectious class. So a class in which they can already spread the virus to others, but they are not developing symptoms yet. Now, of course, there are some people that will not develop symptoms throughout this pandemic as such, and there will be people that develop symptoms, and that's the distinction between asymptomatic and mild infections as such. If you then have mild infections, some people continue to develop severe symptoms, and people developing severe symptoms can be either hospitalized or end up in ICU. Now, both can recover and both can die. So, of course, the condition to actually die is actually that you develop severe symptoms. It's kind of a logical, biological condition. And the one thing that I have to stress here, that some people would say, well, this is not completely consistent with what we know is happening in reality, because, for instance, some people are first hospitalized and then finally end up in ICU. And I completely agree. Though it was not the focus of this specific model as such to really unravel these two sources, we should actually draw another arrow from hospitalized to ICU. But then the problem is you need the data streams to feed into this, because otherwise, mathematically speaking, you cannot discern between the different routes, and the model will collapse in a way that is not desirable. So having said that, it does not endanger the conclusions which you can draw from this model, but you should focus on the right research question or policy question you're trying to answer. This model uses data on social contacts. It uses data on serological studies. It uses data on number of hospitalizations and number of deaths. So that's quite a bit of information that we are all lumping together in this model. And you see the fit to the first wave over here on the left-hand side, top left-hand side for the number of new hospitalizations, and on top right-hand side for the number of new deaths. And that does, well, it's of course a calibration. It does a good job, but it's also a rich model. So we should always be careful not to overinterpret this. What we've done initially, and I'll come back to that in a moment as well, is we looked at the transmission parameters which are underneath this model, and we actually compared these transmission parameters to the social contact surveys we were conducting. And that for us was a true validation of what was happening as such. And that approach, I haven't seen it. I've seen a lot of people using these type of models, fitting it to all the data that they had available, but then neglecting to some extent some of the validation that is necessary to actually see whether this model is truly consistent in getting the dynamics right. So I think that was really an asset of this model, and it's actually the same thing for the two other models, at least in the first wave. Nowadays, we actually use the contact data as an input, but at that time, we actually used it as a validation. What you also see on the bottom is actually scenario analyses that we already developed in April, May. And at that time already, we were predicting mechanistically that a second wave would actually be possible. We had many scenarios. All scenarios indicated there would be a resurgence, but the extent to which also depends on the model and the assumptions. And if you look at S7, S8, S9, these are just 3 out of more than 20 scenarios that we developed. They combine different social contact matrices to actually see what that would result in towards the future. So in that sense, they look at different combinations of the contacts that we make, and we can actually play with that, let's say, to come up with scenarios that potentially could develop. We all know how that went. We know that there was a second wave and a large one, also because interventions were not taken very quickly or quickly enough, unfortunately. So I think in hindsight we've actually came up with a very clear picture that this could potentially evolve like that. Now, what is the key player in the whole study? It's age. Age is one of the key players, the key player. And so I'm in the beginning of the epidemic, I saw a lot of people working on models not taking age into account, and that was the reason why we did not came out with a model very quickly, because we were actually working on a model that took age into account. And why is age so important? Well, we know it because symptoms are age dependent, at least the propensity to have symptoms. Hospitalization is age dependent. People in intensive care, ending up in intensive care, is age dependent. Mortality is age dependent. Transmission is age dependent. And I'll come back to transmission in just a moment. And I can go a little bit further with this. Age is actually the key confounder, let's say, if you want to call it that way, or the key factor that really matters in the spread of SARS-CoV-2. And so colleague Geert Molenbergs worked on a paper trying to estimate the infection fatality rate. Actually, that paper, it took a while basically to get to it, but it has been done very thoroughly now, and it uses some of the features of the model that Steven Abrams developed. And on the right-hand side, you actually see a meta-analysis, a meta-regression that was conducted on studies in different countries, including our Belgian study, showing that indeed the infection fatality rate, so the number of people dying once infected with SARS-CoV-2, is actually very much age dependent. And what you can, if you want to compare it with influenza, seasonal influenza, like a lot of people wanted to do, initially at least, it is very clear that infection fatality rate for SARS-CoV-2 is at least 10 times higher as seasonal influenza. And combining that with the fact that we're dealing with a completely susceptible population for this virus, that actually results in a high mortality if no interventions would have been taken. Leaving alone that, of course, hospitals will be burdened and will eventually, your healthcare system could potentially collapse. And that is the thing that you want to avoid, of course. Now, I already indicated that mixing patterns are really the key ingredient here. And in the early work of John Edmonds, he really collected the first social contact surveys. Also a very big survey in Europe, in 8 European countries in 2006, which was then published in 2008. Was actually done under the lead of John Edmonds, and was my first encounter with infectious disease epidemiology as such, or one of the first encounters. And this is also something I worked on for many years, and on the left-hand side you can see a review of all the data that is available in terms of mixing patterns. On the right-hand side you can see what we've done in terms of this review is we contacted all people that actually did a social contact survey, and we gathered their data. We're still gathering that because it's not so easy, but we gathered that data, at least if we were allowed to, according to ethical regulations and GDPR constraints. And that data has now been made available in what we call a Socrates tool. And the Socrates tool is a tool where you can play with your contact data. You can look at the mixing matrices, and what you see on the right-hand side is actually a heat map of people mixing with people of specific ages. And what is clear from that Socrates tool, I think, is that people like to mix with people of the same age. You also see that it diverges to the working population, where you mix with people of different ages. And then if you look very carefully, you also see the parent-child and the grandchild components. Now, a matrix like that, as such, it's already kind of complicated to model it, because You're asking people to report on their contacts with specific age groups, so there's correlation in the data. And the fact that contacts are reciprocal, if I meet you and you meet me, then yeah, that you meet me, so they need to be reciprocal. So the matrix needs to be symmetric as such. So there are some nitty-gritty details, they're all in there, you can check them. And what you can also do with the tool is you can check what would happen if you put the contacts at school at 0. What would happen if you put your contacts at work at 0, and so on. That is not truly reflecting the intervention as such, because of course, if you put contacts at school at 0, there will be more contacts in other places. People will spend their time somewhere. And that's why we also are now, and that paper is now circulating with the co-authors, we developed what we call a comics Socrates, so a tool that you can also use to look into social contact data that we're now gathering for 20 countries in Europe. So that's on the left-hand side. It's an overview of the countries that are collecting data. The UK has the largest and the biggest set of data. In Belgium, we're second, basically, in collecting these data, and the Netherlands is third. So we have now a new contract through a different route for 26 additional data collections every 2 weeks. And what you can see on the right-hand side is actually the waves as such. So you see those waves in the different colors. That's the timing of the waves every 2 weeks. And then you see the intervention measures that took place. And in our first 8 rounds, we did not have any reports on children below the age of 18 years. That's because our ethical approval had to go very fast and so on. And there were some issues with below 18 years. In the meantime, we are collecting data for children under 18 years, for which the parent is then the proxy to help the child to fill the diary. Now, what we can learn from that is, for instance, and I haven't shown it on this graph, but some people would argue that the HoReCa is not a problem in terms of it will not increase the number of contacts. Well, using these type of data, we can actually show that it's not true. HoReCa is indeed increasing the number of contacts people make, but what is often difficult is to really estimate to what extent are people increasing their contacts. And of course, especially given intervention measures and preventive measures in place. Nevertheless, these data, that is the data that we've been using to validate what we've done. And these are have shown to be instrumental also in the current modeling. Now, if you bear with me, I'm going to talk for a brief moment and then go into the discussion more, but brief moment on variants and vaccination. Now, so what we noticed was indeed that this British variant, the B117 variant, was really growing quite quickly in Britain, in Ireland, in England, in Wales, and so on, over the end of the year period, and especially also in January. And what we saw there was a huge growth advantage compared to the old variants. And I really like to call them the old variants, because it's not only the Wuhan variant anymore. That Wuhan variant actually developed quite soon in another variant that was spread all over the world. And this British variant was shown to have an advantage in terms of transmission, but also increased severity as such. So what did we do? We used data on S-gene dropout, which is a good proxy for the British variant. I'm going to spare you the biological details about that. It's a bit more tricky, but really today, if you have an S-gene dropout, you can 99% certainty assume it's the British variant. So in that sense, it's a very good proxy. We used the contact survey data that I just discussed very briefly. We used serological data. And we used hospitalizations and deaths. And on the right-hand side, you see what we've done to the model is we also included vaccination according to the vaccination schedules that are now being rolled out actually. And so we doubled the model that we had just a moment ago. So this model has been doubled, but now we added the vaccination components where people, if they're vaccinated, they actually go to the R class quite quickly. So they go to the recovered class. We also had and not all the arrows are shown on this picture, but we also had a situation where we had the British variant in place. And so where you have this increased transmissibility in place. And we fitted that to the S gene dropout data together with all the other data as such. And in terms of the results, well, 2 weeks ago, we came up with this kind of picture. So first wave in terms of daily hospitalizations, second wave. So we fitted it to those data until the dashed line over here. And then we started predicting what would happen further. Now, one thing that we could not explain was quite a quick increase in the number of new hospitalizations. And we could not explain it because the measures were still the same at the beginning of March. So something else was going on. And we checked that the measures were, or the contact data indeed indicated that the measures were actually followed fairly well, although we did see a little bit of a fatigue in terms of contacts in the home, contacts inside, which were more risky at that time. They increased a bit compared to contacts outside. Now, at that time, this blue curve was the curve that we assumed initially, and the rise in there was completely explained by the British variant. But we could not, with that model, we could not explain why the number of confirmed cases were actually really going up very quickly. And so we came up with two alternatives, one in which we assumed, no, there is indeed additional transmission compared to that yellow scenario, and it's the blue one, 10% extra transmission, and the red one is 20% extra transmission. And these are really scenarios, of course. And what we actually, with a few more data points, we could actually estimate that the most plausible trajectory was actually the 10% trajectory. But of course, very dodgy, a huge amount of uncertainty still. And so very difficult to make any decisions in whatever direction. Now, a second thing we've done, we also played with the vaccination schedules. And so the fit that I was just talking about is the middle panel. But we also had a more optimistic panel on the left-hand side, which is the panel that corresponds to the original vaccination schedule. And on the right-hand side, we have a panel where we actually left out quite some vaccines in the assumptions that the scenario would be much more pessimistic. And what you do see is for this third wave that we're actually confronted with now, you do see there's quite some difference, and especially if you look at the extremes. It's sometimes 100 admissions per day difference. And of course, that's really tremendous if you think about that, because that would actually mean it's not only the admissions that count, it's also the area under the curve that counts, because those are the people filling up your beds in the hospital for quite a period. And I'll come back to that in just a moment. So the key question here is, should one intervene? And if you look at the middle picture, should one intervene? Of course, vaccination is what it is. In terms of, I mean, people are of course trying to get more vaccines, but they have come in quite slowly, I would say. And let's hope it doesn't deteriorate, that we do not move to something like the red scenario. But in this scenario, in the middle scenario, you could ask yourself the question, and some people would argue, well, this wave doesn't look as bad as the first and the second wave, so we're fine. We don't need to intervene. It will go down. Why? Because of Easter holiday and because of vaccination. Well, to some extent, you're right, if you look at this picture. But the real surprise, and I'll come back to that in just a moment, the real surprise was really an incredible increase in the number of ICU beds taken. Now, let me illustrate on first of all, what it does on the daily hospital admissions if you would intervene. And what we took was a lockdown like it was implemented in October 19 to 25. At that time, schools were not yet closed, to make that clear, but the other activities were actually cancelled for 4 weeks. To a large extent, they were cancelled. Not everything was cancelled. We know the whole discussion about non-essential shops and so on, but I will not go into detail there. But what you see is that you can have a drastic decrease if you take similar measures as were taken in October. And that decrease, some people would say, wow, that's remarkable. I don't believe it. Well, look at the decrease we had on a second wave. That was even steeper than this one. So despite of the British variant, which is much more difficult to control, we still have a very steep decrease. Of course, this is a scenario. This doesn't resemble what has been decided by the policymakers in Belgium. And the second thing is that fatigue is likely to settle in. So this is maybe a very optimistic scenario. And that's why, and I'm not showing it here, I'll show it in just a moment. We also had a scenario where you assume that people make 30% more contacts. Just to show you what fatigue could actually result in. But the remarkable thing here, I think, is the size, basically, not the peak. The peak is more or less the same. And why is it the same? Because interventions were not taken early enough to make a difference between both. But the size of the peak, well, sorry, the width of the peak, let's say, the area under the curve, is very different for the two. And that is something that you can translate for the left scenario, where we do nothing, and for the hospital load over here, and for the ICU load over here. You see there's a lot of uncertainty, and we propagate uncertainty. There's a lot of uncertainty related to that. But nevertheless, for hospital load, it's still pretty high, and the extremes are really living up to the second wave. But for ICU load, relatively speaking, it's even higher. If you just compare ICU load from the second wave that is on the left-hand side and from this third wave on the right-hand side, you could really actually go up quite quickly. Now, the average curve, which is really not a stochastic realization, it's an average of curves to allow people to picture where the mass of these curves really is, shows that we could maybe maintain it at 1000, but equally fine, there is a huge amount of uncertainty. And today we already know if you put the dots today, you will not end up in the lower end. You will likely end up in the larger end. And that's, of course, a concern. This would also mean that after Easter holiday, or after this period of 4 weeks, you cannot open up very quickly, because then it will actually potentially rise again. So you need to wait a longer time to actually intervene. And that was one of the reasons as well why policymakers decided to intervene, because they wanted to say, like it's done now in France as well, they wanted to say, let's lock it for a few weeks and then we open up, and then we'll be in a much better place. Well, the key question is what will happen in the next few days and weeks. But one thing I'd like to indicate here as well, and maybe I should have done it here, is that in the second wave, we actually ended up at a large plateau. We were still very high. The model that we had at that time did not forecast that. That was not following the scenario we actually came up with. And the reason for that was actually fatigue. We saw that in the contact surveys, that there were certain age groups that really made a lot more contacts than before. And that was really explaining why we ended up in this large, on this large plateau. But we were somehow successful in keeping in that level and not going up again. And that's, I do think, and I'm quite sure actually, due to some of the measures that were taken to prevent people from traveling too much at the end of the year and so on. Now I'm going to end here with the scenario where we do intervene, and then you see you're in a much better place when you go down. So I think that is really hopeful. Let's see what will happen. Honestly, we're not sure. We should reach the peak in a few days, end of next week, I think, in terms of number of hospitalizations. We see that we're already reaching the peak of the number of contaminations. So let's hope it goes down quite quickly. And this is just an evaluation of the data that were available until yesterday. And actually the data that will be announced tomorrow, I think they're more or less complete. So tomorrow, the new number of new hospitalizations is 295. there will be a confirmation later on this afternoon for that. But you see, we're still following. We're still not decided in which trajectory we're really following, and there's a huge amount of uncertainty as well. On the left-hand side, these are the two scenarios that I've shown previously. On the right-hand side, the gray one is the one where we allow 30% more contacts compared to the blue one. So, of course, we all hope that we're going to follow the blue one. Maybe seasonality, which I haven't taken into account in this model because it's kind of complicated, will help us a little bit to that extent. And then so this is where we are at this moment. Of course, we're reworking the model and so on. We'll be calibrating this again this weekend. But in terms of models and communication, I think it's important that people realize that these are not predictions. These are scenarios, and that's a big difference between the two. And then the second thing is I just wanted to bring this review to attention, that we are also working with other groups to get to what we call ensemble methods, looking at different models with different assumptions, not to rely only on one model. I can honestly say that this model has performed the best out of the models that were there, but nevertheless, it's still very much important to work with different models and to discuss the pros and cons of the different models. And the one model that, if you read this paper a little bit further, what is very important, I talked about validation already, but I don't know whether you're familiar with the White House model, the model that has been used by IHME to look at what the disease would do in the US. It actually predicted or forecasted in the first wave that it will all be over in a few weeks. If you ask any person, sensible person working in this field for a longer time, you would have known that it would not have been over in a few weeks. So it was kind of remarkable that they came up with a model like this, and that they were quite wrong in their forecasting. And I think one of the reasons is, and it's not to point fingers, but it's really to follow the rules, let's say, of sticking to your field. And of course, you can interact with others. And I think I'm very open to that. And I really would encourage people to do that. But to really think twice about what you're actually putting forward as a model outcome. They have improved their model considerably. So it's much more, and it's also now in line with what we do. Their results are very similar. They're also applying this for Belgium. The only problem, of course, they've burned their name, unfortunately, and that's an issue. So not for some people, they're still okay, but for other people, they really burned their name. And I think there are other examples of that as well. So So I think we've done a good job as such as a group, as such as working on these models, but that doesn't mean we will be right in the next few weeks to come. And you need to be very modest about that. We are trying to help, basically. Why? Because we don't want to have experiments with the population without running these type of models to show some basic insights at least. But don't take them as predictions. That's my warning message here. So I'd like to end with the sources if you want to look up more information and so on the left-hand side. There are different sources. And on the right-hand side, linked to 2 citizen science projects. Maybe if you've heard of the large corona study, which has been tremendously successful with over 3 million people answering the questionnaires. We believe it's about 500,000 unique persons that participated. We're still at about 20,000. So that's really great. And then we've launched also Infectieradar. So I truly invite you to participate. Infectieradar actually looks at pathogens as a whole, respiratory pathogens, but you can fill in your own diary. You can keep track of what you are experiencing. And you can actually also look at where are the infections and are there any infections close to me. It has been launched, this week, basically. So We're still recruitment phase. But the more people we have, the more we can learn from this. Of course, taking into account all the biases in participatory studies and so on. But we have good experience in that, so I don't see issues there at this point in time. And then I would like to thank you for your attention. Thanking also the collaborators. Thank you.
Thank you, Niel, for your excellent presentation. We run a little bit out of time, but let's say we can still have like 10 minutes for posing some questions and discussion. If I maybe I can ask the first question. Different people that are present in this room, like for instance me and Eric, we have developed transportation models based on individual mobility. Could they be used as a complement to improve the models you were presenting?
Yes, I think so. I think it needs a bit more research how to do it exactly and how to integrate it exactly, but I think it would be very useful. Especially also for SARS-CoV-2 because it's very super spreading like. That means it's very patchy, but we've seen, for instance, some divides, let's say, in terms of the analysis we've done, or in terms of the disease incidence in different places in Belgium. And I think if they could offer a picture that corresponds to that, that would be really great. We've also seen, for instance, the axis Brussels-Antwerp being very prominent in terms of disease incidence. And that actually also corresponds to travel behavior, I think, very much. So yes, indeed. So I think we should, if time permits, this would be really nice to talk in more detail about that.
Perfect. Then I saw Mauro putting his hand first.
Yeah, thanks a lot for the very insightful talk. It was a very nice review. I have a question which has been bugging me for a while. In these models, I mean, you did underline a big issue, which is people's fatigue and behavior, right? We're observing more cases than we would expect because people are kind of need social context and therefore they see more people. What's the approach you use to model this kind of processes? Do you use scenarios or do you have kind of dynamic variables representing that?
Yeah, so what we can't do is predict how, to what extent people are indeed tired of all the measures and so on. What we can do is through these social contact surveys, we can learn whether people follow up the measures and whether the realizations basically of the contacts are still following the same pattern as it was done a week or two weeks ago. So you do learn quite fast whether people are losing grip, let's say. And so, for instance, this week we had our survey has run on Wednesday, and we're now analyzing the data. We will have results today, and this will give us kind of an indication of what will happen in the next 10 days to come, let's say. The key question is then, of course, will this fatigue effect increase or not? And that's something we can't answer, and that's why we do sometimes get 10%. We assume additional contacts for 10% or 20% or 30%. But we do use these social contact surveys as a guidance tool and a validation tool. Yeah.
I see a question from Eric.
Yes, thanks for the talk. I'm wondering if each time you run the model for a few more net weights, did you rely on the same base population at the start, or do you update your population each time according to the events which have been occurring in the past time?
Yeah, so the population is updated in terms of their infection status and also in terms of mortality. So that's all included. So we're keeping track of immunity profiles. So for instance, what we can estimate nowadays is that we're at about 27% of people in Belgium have experienced COVID-19. So we do keep track of that, yes. It's very important because if that is not correct, whatever you predict, so there are models, people using models that have a lower immunity profile, well, then you would predict waves that are much higher, too high, and unrealistically high. And how do we do that? Well, that is using serological data. We do have serological data. We can also use the serological data collected by Cienzano from blood donors. They have their own issues, so you should be careful, but they actually give you your boots in the ground, let's say, in terms of what is realistic. Yeah.
Okay, thanks.
Maybe the final question for Dirk.
Thank you, and also for the excellent presentation, and of course, most of all, the excellent scientific work that is being done. So I'm working in the field of mobility transport, and I have two questions. One discussion is, of course, the public transport and what is happening on public transport. Is this taken on board in your research in any way? That's my first question. And the second one is on the type of mobility, the purpose of traveling. So you mentioned, I think, the homework and the homeschool travel, but we know in Flanders, at least in non-COVID times, this type of mobility represents only 1/4 of the mobility. 3/4 is more in recreational and shopping sphere. Is this taken into account too? So shopping, recreation, for example, to the coast, is this taken into account, or is it envisaged to take this into account in your modeling work?
Mm-hmm. Okay, thank you for the questions. First of all, for public transport, what is always the issues in infectious disease EPI is you cannot measure infections on public transport. People go home and they will rarely indicate that they have been infected at public transport, simply because they can typically also not recall anyone being infected, or so there's a lot of uncertainty about it. So also in the past for influenza, people indicated that public transport is likely not the key driver as such. I think that's correct, but honestly, I think it's also because of a lack of data, of good data about that. A second thing on the transport that we take into account, in the different models, it's done differently. So in the stochastic model, we do not take transport into account. It's a national model. So that's the disadvantage of that model. You can't use it at a granular scale. In a metapopulation model, we do take it into account, not as granular as it could be. So that's still work that can be done. And the key question is whether you then do it in a metapopulation model or in an agent-based model. But in the agent-based model, some of these things are nevertheless taken into account. So as I indicated, children traveling for school and so on, they're taken into account. So small children travel a short distance, other children travel a lot further, longer distance, and so on. And we do have the relationship between distance traveled and number of contacts from a social contact survey we conducted. The only problem was we were still working on that. And so we're trying to write it up as we go along during this pandemic as well. Because I think that would be also for you, I think that would be a really useful tool to see where we maybe can make connections as such. And having said that, it's the leisure activities that are the most dangerous ones in terms of disease transmission, because they're frequent as such, but it's not very frequent with the same person. It's often with different persons. And so in terms of disease networks, it's really, it allows the disease to travel very quickly through the network as such. And that's truly an issue. Yeah.
So let's all thank Niel again for his excellent presentation. I look forward to see you all also during the next event of the lunch talk. So the next one being the 30th of April, and to see you during the transport research days. So let us thank and applaud Niel once more. So thank you, Niel.
Okay. Thank you, everyone. Take care.